All right, so this video we're going to talk about compiling our intensity data. So imagine you have hundreds and hundreds of files, and each with these normalized intensity measurements, or rather these raw intensity measurements. And we now want to bring all of them together in a, say, an Excel file. So we've built this function in under review compile results set. Here we need to tell the program the channel name. In this case, let's do FITSI. You could do DAPI or FITSI for our sample analysis. Again, the conversion factor, and then a lower bound and an upper bound for where we're going to be normalizing our data to. So we pick a distance that is far enough away from the explanted device interface that the tissue response has returned back to baseline. And if you go back, for example, let me go back and open this up for you. You open up a few of our intensity plots here. You can see that our response is dropping to baseline rather rapidly, and this also follows with all of our other analyses that we've done. And so a typical background that we've done in some of our analyses is just 400 to 450. So let's go ahead and pick that this time as well. Okay, so we're going to say 400 to 450. And then it asks normalization, 0 or 1. Okay, so this is FITSI, and FITSI was our GFAP channel. And so the normalization for 0 or 1 is really difference between proteins that are constitutively expressed, or rather markers that are constitutively expressed versus those that are not. So for example, astrocytes, GFAP is constitutively expressed. We would see, even on normal healthy tissue, staining throughout the brain, but it would just be at a baseline level, or a 100% or a 1 level. CD68, which is a stain for activated macrophages and microglia, is not normally expressed at considerable levels in the brain tissue, and so that we would normalize to 0. So for this analysis, GFAP, we will normalize to 1 and group width of 50 microns. So this is going to be our bucketing intervals. Okay, we'll select OK. And again, we need to find our data. And in this case, we actually select, rather than selecting images or folders of images, we're going to select the folder that contains the folders, if that makes any sense. So in this case, we're going to select demo. And what the program is going to do is search through all of the subfolders in demo for files, rather of folders that contain the sconfig files. And if it finds an sconfig file, it'll try to analyze an analysis results file that's there. Okay, once the analysis or the compilation is complete, you get a little message saying it's done, and it has created a file in this directory, demo compiled second results. Okay, so we can go over there. And we have this file, compiled second results. So this file has a number of tabs. Sheet 1 is blank. XD min and XD max, these are sanity checks, right? So these are, oh, and I actually had multiple test images in. So I had a test images folder here, and I had another test images folder down here. So, like I said, when it selects, when you tell it, it looks in all subfolders for those sconfig files. So we'll get to compare them, two separate analyses, see how close they are. So this XD min is the minimum pixel distance in that bucket. Okay, and it's in pixels. So if we take these values and multiply by our conversion factor, which is 0.625 microns per pixel, that will convert these numbers to microns. And so you can see our minimum should line up with our minimum of our bucket. So this is the 5 to 10 bucket. It should line up 5, 10, 15, 20, 25, 30. So that's great. Okay. XD max. This should do the same thing. This should line up at the high bound. So 0.625 times this number. So that's close to 5. That's close to 10. That's close to 15, etc. And so because of rounding and discrete pixel approximations of distance, these are never going to be exactly spot on with these numbers up here. But they should be pretty close. And this is just a sanity check to make sure that there isn't anything weird going on. And if you have exclusions, large exclusions that take up a lot of area, sometimes these might look weird. So it's always good to kind of scan through and make sure these look consistent. And then mean is simply just the mean pixel distance in that band. So this should be roughly 2.5, etc., etc. Number of pixels. This is the number of pixels contained within this band. So the 0 to 5 band, there are 3,500 pixels roughly. Again, this is a good sanity check, especially if you have lots of exclusions. And so this is obviously going to be increasing as you expand. More pixels, the larger you get, until you get out to the furthest extents, and then you can see it starts to decline because you have a square box. So you're starting to clip corners here. Okay, the next tab is normalized intensity. So this is at our 5 micron intervals, the intensity in that bucket divided by the intensity in the 450 excuse me, 400 to 450 range. Okay. And finally, we have normalized intensity area under the curve. So we basically take the normalized intensity on the 0, 5, 10, 15 discrete range, and then take the area under the curve, Riemann sums style, to determine what the overall intensity is in each of these buckets. So 0 to 50, 50 to 100, and you can see this declines rapidly. Okay, so that's that. This is what a typical analysis file would look like, and this is obviously the same image twice, but something that I will frequently do, I'm just going to add a couple more so it looks more like a data set. I will sometimes add, not sometimes, always, add a couple columns here that describe what these are. So we always run our analysis completely blind to what these samples are. So, this would be animal A slice 60, A slice 30, A slice 10, B slice 4, B slice 10, B slice 60, whatever it is. If we randomize slice number, we randomize as much as we can and blind as much as we can. But then I'll create some helper columns here that tell me what group it is. So this will be animal, and then group. So this could be animal A, B, B. Okay. And then if you have a small number of animals, it might just be easy for you to go look at your lookup table or your legend if you've blinded yourself, and then say, okay, A was my treatment 1. Okay. And this, I looked it up and was my treatment 2. Okay. You could do it that way. My preference, especially because we're doing large numbers, I'll create a lookup table. So this would be, my animal and my treatment. And so animal A, we said, is treatment 1, and animal B is treatment 2. And this I can name lookup table. Okay, and then when I go over to my sheet here, I can either automatically grab this by saying left this text, comma 1. And what that does, if I delete those, you can see that's going to grab my left character and scan that down. And then same thing with group. I can now say equals the lookup. And I'm going to look up the value A in table lookup table. And I want to grab the second column. And it's always a good idea to say false, which is just telling it to look for an exact match. Okay, and that will look up my treatment group. If I drag that all the way down, treatment 1, treatment 2. And so this is a really helpful trick if you have a large data set, lots of slices, as we do. Okay, and then you can take this data directly into your statistics software of choice to do the analysis. All right, so I hope this was helpful. I appreciate your time, and always feel free to reach out if you have any questions. And maybe I'll upload some more videos in the future as time permits. All right, thanks for listening.